Swastiastu. Assalamualaikum warahmatullahi wabarakatuh. Salam nama budaya. In this video, I will explain about chapter 6. But the first, I want to introduce myself. My name is Putra Hutabarat. With student ID number 23055310075. I'm from Mechanical Engineering Study Program from Engineering of Faculty from Udayana University. Okay, chapter 6 is Fabrication and Finishing of Metal Products. Metal products that undergo mechanical reduction operations after casting are called work products. These products can be shaped, finished, and assembled using a variety of metal processing techniques. The possibilities range from high volume metal production figure 6.1 to the manufacture of complex parts by powder metallurgy figure 6.2, or the joining of the thin foil by ultrasonic welding figure 6.3. Next, 6.1 Deformation processes. In metalworking processes, a workpiece such as a billet or a blanket sheet, for example, can be plastically deformed by a set of tools or dies to obtain the desired final thickness and geometrical configuration. Metalforming processes can be classified into two general categories: bulk or massive forming operations, bending and sheet forming operations. Metal forming equipment. Metal forming is done with a large variety of machines or equipment such as rolling mills for plates, strip and shapes, machines for profile rolling from strip, ring rolling machines, thread rolling and surface rolling machines, magnetic and explosive forming machines, drum benches for tube and rod, wire and rod drawing machines, machines for pressing type operations. Next, the significant characteristics that comprise our design and performance data proportion to the economical use of these machines include characteristics for load and energy, available load, available energy and efficient factors, which equals the energy available for workpiece deformation or energy supplied to the machine. Time-related characteristic, number of strokes per minute, contact time under pressure, and velocity under pressure. Characteristic for accuracy, for example, deflection of the ram and frame, particularly under off-center loading, and press stiffness. Hot and cold working. Metal can be mechanical worked over a range of temperatures. Higher temperatures can improve workability characteristics, although many work products are cold worked in order to achieve certain mechanical properties, or sometimes they are warm worked to worked for other specific purposes. Next, the grain is in cold worked material also become distorted, elongating in the primary direction of the deformation, such as the rolling direction in cold rolled strip figure 6.6a. Impurity passes in metals and alloys can deform and alloys during hot working, acting as reinforcing fibers to impact microstructure and material properties figure 6.7. Next, point 6.2 Primary production mills. In primary production, the initial stage of metalworking involves bringing the cast structure into working shapes. The starting material is usually bars from static cast or continuous cast. Some ingots are still printed statically because not all fair use and non-fair use metals can be printed continuously. The raw and weak structure of the ingot limits the temperature range for forging. Forget a temperature higher than 3/5 of the absolute melting point of the element. Rolling mills. Rolling can be done at different stages in a production mill. The first stage uses a primary rolling mill, which is large and expensive. Smaller secondary mills are used for further reduction. Continuously cast ingots can go directly into secondary mills, but products like sheet, plate, or strip are first rolled in primary mills. Then further reduction is done using cylindrical rolls. This can be done in a single mill or a series of mills. The resulting strip can be coiled for later use or cut into sets. Good rolling of thin sheet and strip. Thin sheet and strip with high quality surface finishes can be produced by cold rolling. Production begins with strip from the hot rolling mill. Before cold rolling, the metal usually must be acid pickled to remove surface oxide or scale produced during hot rolling. In pickling, scale is removed by chemical or electromechanical means. Next, sheet and strip may be annihilated at intermediate stage of reduction or after the final reduction. Typically, this process takes place in a controlled atmosphere to keep surface free of oxidation and scaling. When a metal bar is rolled, any increase in width is minimal. However, the metal becomes thinner and larger. For all practical purposes, during plastic deformation, the volume of the metal does not change significantly. Contour roll forming, also known as cold roll forming, is done to form sheet and strip into shapes with nearly uniform cross section. Rolling stock is fed longitudinally through a series of roll stations with contour rolls, sometimes called rolls dies. All metals suitable for common cold forming processes can be contour roll formed. The list includes carbon steel, stainless steel, aluminum alloys, and copper alloys. Titanium and nickel-based super alloys are more difficult to contour roll form. This type of operation is performed less frequently of these alloy systems. Next, 6.3 Forging. Forging compresses metal to change its shape or size. Large forgings are made in primary mills, but forgers also buy work products for further forming. Common forged products include cranks, halves, wrenches, hammers, rotors, and landing gear. Open die forging is a process using progressive blows between anvils to shape a metal workpiece without the use of dies or confinement. Closed die forging, also known as impression die forging, shape hot metal within the two enclosing dies, allowing for complex shapes and precise dimensional tolerance. The importance of material flow knowledge in die design and the use of computer models and expert systems. Friction limits the minimum thickness of the web. Defects in forging can occur due to improper metal flow and other factors such as the initial shape of the workpiece, wood mold design, and lubricant selection. All of these factors can cause defects such as creases in the metal when forging. In die design, knowledge of material flow and the use of computer models and expert systems are essential. Friction limits the minimum thickness of the web. Lack of metal flow and other factors can cause defects in metal processing. Next, radial forging. During radial forging, the material is forged between four dies that are arranged in one plane with two opposing dies acting of the piece simulation, Osley picture 6.14. This approach eliminates the spreading observed in open die forging and restricts expansion of the material primarily to the axial direction of the part. Hot U-shaped forging enlarges and reshapes bars or tubes, increasing internal soundness of anodes before open die forging. Cold forging has advantages over machining as a part-making process. Waste material is not generated. Machining produces shapes. The tensile strength of the forging stock is improved, and grain flow can be controlled as in conventional forging. Wire for cold heating generally is available in 5 levels based on surface quality. In order of increasing quality and cost, they are industrial quality, cold heating quality, researched heat or scrapless node quality, special heat quality, alternate ground or safe wire seamless. Coning is compression process to press or hammer design onto a workpiece. It creates detailed and accurate products like coins and patterned tableware. Next, 6.4 Drawing and extrusion. Drawing and extrusion involve pulling and pushing sections chalk dies to decrease cross-sectional area or shape of materials. Drawing is one of the oldest metal forming operations to make long products with excellent surface finishes, closely controlled dimensions and constant cross sections. Extrusion is a deformation process used to produce long, strength semi-finished metal products such as a bar, solid and hollow sections, tubes, wires, and strips. The favorable compressed safe state of stress during extrusion allows a high capacity for deformation, and so it is possible to extrude metals that can be only slightly deformed by other methods. Hot extrusion technology. Pre-rolled bills or round ingots can be worked in an extrusion press, which is an open-ended die. A ram moves the metal through the die, which determines the shape of the extrude shape. For hot extrusion working, the bile temperature is typically greater than the required to sustain strain hardening during deformation. This is generally greater than 16% of the absolute melting temperature of the metal. Next, cold extrusion. In this process, metal is sequenced or squirted through a hole in a die. Long melting point and relatively ductile metals such as aluminum, tin, and lead are easily extruded. Next, 6.5 Forming. Steel tubes, plates, and sheet metal are formed through folding, stretching, and pulling operations. The folding process is mainly used to shape steel and tubes. Sheet forming involves different folding, stretching, and pulling operations, as well as special methods for developing surfaces with deep or shallow grooves. Springback is a major factor in forming operations. As an example, consider a simple bed picture 6.17. The tensile stress is a maximum of the outside surface of the band and decreases toward the center of the sheet's thickness. Methods to overcome or counteract the effects of springback are overbending, bottoming or setting, stretch bending. Next, bending of bar and tube. The four basic methods of bending bar and tube stock are compression bending, draw bending, stretch bending, roll bending. In compression bending, one end of the workpiece is fixed in place relative to a stationary bending form, while a movable saw or roller compresses the section and changes the form. In draw bending, the workpiece is clamped to a fixed form and a whipper saw revolves around the form to bend the workpiece. Feature 6.19a. Next, sheet forming. The various types of sheet forming operation include shearing to lace, to slit narrower strips, separate parts, cutting off, parting, cut out a part, blanking, or create a hole or punching. Next, bending of blanks in press brakes of power slide machines or by roll forming for mass production of corrugated sheet architectural sections and log seam and welded tubes. Straight forming of blanks by firmly clamping much or all of the circumference and stopping by the penetration of a punch at the expense of thickness. Embossing is a highly localized form of stretch forming. Deep drawing of parts with recessed contours by forcing sheet metals between dies, usually without substantial thinning of the sheet. In contrast, the stretch forming, the shape is developed by drawing material into the die while a average thickness is approximately preserved. Spinning of sheet metal or tubing into seamless hollow cylinders, cones, and hemispheres or other circular shapes by a combination of rotation and force. Manual spinning and power spinning are both done. Explosive forming for pulling or reducing tubes and for forming shapes similar to those produced by stretching. Next, the mechanics of deep drawing of a conical cup are illustrated in picture 6.22, which shows the complexity of the process. Deep drawing involves many types of force and deformation modes such as tension in the wall and the bottom, compression and friction in the flange, bending at the die radius and strengthening in the die wall. Spinning sheet metal or tubing can be converted into seamless hollow cylinders, cones, hemispheres, or other circular shapes by a combination of rotation and force. Two methods are used: manual spinning and power spinning. Typical shapes produced are shown in picture 6.24. Next, 6.6 Powder metallurgy. Powder metallurgy or PM is a growing branch of metallurgy based on the production of material in the form of metal powders and the manufacturing of parts from these materials. Powders of metals and alloys are used to create complex shape parts with close tolerance, control density, and unique properties of PM methods. The common two-step process involves powder compaction and densification through pressing and sintering. While other methods include metal injection molding and high temperature compaction techniques. Sintering is a process where a metal powders are heated in a furnace, bonding the particles and shrinking porous and acid densification. It is usually done on compact powder but can also be used on loose powder for specialized applications. Fabrication of parts by PM methods has several advantages that include producing parts with more uniform microstructure and distribution of alloying elements, high volume production of parts with natal shape or near net shape dimensions, thus reducing the need for machining, flexibility in component design. Next, design flexibility with PM is quite remarkable in the production of parts with many grooves, tapers, curves, picture 6.25. Next, 6.7 material removal processes. Material removal processes including machine tooling are used to achieve high precision and controlled surface results. Machine tools are used to change cast objects, develop objects, or metal blocks into the desired shape. Machine tools are expensive because they are slow and require large investments in skilled labor. However, it is driving increased productivity with better cutting machines, improved design, better tool materials, and an understanding of how workpiece affect machine tools, cost, and quality. Next, there are three basic classes of material removal operation: conventional machining operation, turning, drilling, milling, boring, planing, shaping, reaming, and tamping, where material is removed from the workpiece in the form of a chip. Abrasive processes such as grinding and honing, where small particles are removed from the workpiece by abrasion with a hard tool. Abrasive processes have lower material removal rates and higher energy requirements than conventional machining processes, but can produce close tolerance and finer surface finishes. Non-traditional machining processes, which include electrical discharge machining (EDM), electrochemical machining (ACM), and ultrasonic machining (USM). Next, machinability varies most significantly between different material classes or base chemistries. The common classes of metallic work materials in general order of decreasing machinability include magnesium alloys, aluminum alloys, copper alloys, cast irons, nodular irons, carbon steels, low alloy steels, stainless steel, hardened and high alloy steels, nickel-based super alloys, titanium alloys. Next, when possible, materials from classes higher on this list should be substituted for those lower on the list if machinability is a primary consideration. Surface integrity involves the study and control of both surface roughness, topography, and surface metallurgy. Examples of typical surface integrity problems created in metal removal operations include grinding burns on high strength steel aircraft landing gear components, untempered martensite in drilled holes in steel components, grinding cracks in the root sections of cast nickel-based gas turbine buckets, lowering of fatigue strength of part processed by electrical discharge machining, distortion of thin components, residual stress induced in machining and its effects on distortion, fatigue, and stress corrosion. Next, 6.8 Joining processes. Joining involves the use of mechanical, chemical, or physical force that keep two parts together. Mechanical methods are based on various types of mechanical fasteners, while adhesive bonding uses chemical bonding, perhaps with some physical or mechanical factors. Physical methods of joining include welding, flashing, and soldering. The focus here, by necessity, is only a brief overview on the wide-ranging technologies of welding, pressing, and soldering. 6.8.1 Welding. The two basic categories of modern-day welding methods are fusion welding, where the workpiece metals are melted in the joint region and allowed to resolidify to form a metallurgical bond. Solid-state welding, like forge welding, where some heating without melting and mechanical force allow the formation of a physical or interatomic bond of the two metals. Next, silent metal arc welding (SMAW) is a manual process where an arc is generated between a flux-covered electrode and the workpiece. This includes decomposition for shading and protection. It originated in the 1800s and gained popularity in the 1930s in the welding industry. Gas metal arc welding (GMAW), also known as metal inert gas (MIG) welding, differs from the SMAW process in that its electrode is a bare solid wire that is continuously fed to the weld area and becomes the filler metal as it is consumed. In contrast, SMAW electrodes must be discarded when they reach a minimum length. Gas metal arc welding is widely used in semi-automatic, machine, and automated modes. Next, okay, that's the last. I think that's I can explain about chapter 6. If there are errors in reading, please forgive me. Thank you for watching my video, and thank you.